Hello, this is Dr. VC Sontake and I am going to take the course Heat Transfer. Objectives of this video lecture are to discuss and evaluate overall heat transfer coefficient of heat exchanger and to define fouling and its effect on overall heat transfer coefficient of heat exchanger. Overall heat transfer coefficient U. Let us consider a tube-in-tube heat exchanger in which inside tube is carrying hot fluid and outside tube is carrying cold fluid. The heat transfer from inside fluid to the inner surface of the inner tube will be by convection, and this hot fluid, that is inside fluid, will offer resistance in the form of convective thermal resistance, and it will be given by 1 over HIAI. The heat transfer rate from inner surface to the outer surface of the inner tube will be by conduction, and this surface will offer conductive thermal resistance to the path of the heat flow, and this will be determined by the cylindrical conductive thermal resistance offered by cylindrical surface. And finally, heat transfer from outer surface of the inner tube to the cold fluid will be by convection once again, and this fluid will offer convective thermal resistance to the path of the heat flow, which will be given by 1 over H naught A naught. So let's say AI represents surface area of the inner surface of the tube that separate two fluids, that is hot and cold fluid, and this will be given by 2 pi RIL or pi DIL, where Ri and Di are the radius and diameter of inner surface of the inner tube. Similarly, AO represents area of the outside surface of the tube, and it will be given by 2 pi ROL or pi DOL, where R suffix O and D suffix O represent radius and diameter of outer radius and outer diameter of inner tube. These inside and outside area are represented in this diagram. Let HI represent heat transfer coefficient of inside fluid, in this case hot fluid, and it is given in watt per meter square Kelvin. HO represents heat transfer coefficient of the outside fluid, cold fluid in this case, in watt per meter square Kelvin. K represents the thermal conductivity of the tube material, inside tube material particularly. So the total thermal resistance offered to the path of the heat flow by this entire tube-in-tube heat exchanger will be summation of thermal resistance offered by hot fluid, inside fluid, that will be convective thermal resistance offered by material of the inside tube, which will be conductive thermal resistance, and thermal resistance offered by outside fluid, that is cold fluid, and once again it will be convective thermal resistance. So it will be given by 1 over HIAI plus log of RO over RI to the 2 pi KL plus 1 over HOAO, where this term represents conductive thermal resistance offered by cylindrical wall. Now, rate of heat transfer from hot fluid through the wall to the cold fluid can be given in terms of temperature difference between hot and cold fluid and total thermal resistance, which can also be written as in terms of overall heat transfer coefficient as U into A into delta T. In terms of inside area and outside area, the equation for heat transfer rate can also be written as U into AI delta T is equal to U into AO delta T. Now, the question comes to one's mind why there are two overall heat transfer coefficient in case of cylinder. So I will come to that point. So U into A is equal to 1 over R total, or in terms of inside and outside area, overall heat transfer coefficient will be Ui and Uo. So 1 over Ui into Ai is equal to 1 over U naught, A naught is equal to R total. So question comes why there are two overall heat transfer coefficient for tube-in-tube or cylindrical type heat exchangers. So explanation to this point is that in case of cylindrical heat exchanger, inside and outside area of the tube, particularly inner tube where actual heat transfer is taking place, are not same. Though product of UiAi will be equal to U naught A naught, but Ui will not be equal to Uo. So it depends which area of the tube you are taking into consideration. So accordingly, overall heat transfer coefficient based upon inner area or outside area will come into picture. So simplifying this further, 1 over Ui Ai is equal to 1 over U naught A naught is equal to 1 over Hi Ai plus log of Ro by Ri over 2 pi Kl plus 1 over HOAO. So this is the relationship between overall heat transfer coefficient based upon either inner or outer area and total thermal resistance offered to the path of the heat transfer in case of tube-in-tube heat exchanger. So U is meaningless unless area is specified. So I have to define whether I am taking U based upon either inside area or outside area of the inner tube. Now let us consider the different cases. Case number 1, if resistance offered by the metallic wall or material of the inside tube is 0. That is possible when the thermal conductivity of the inner tube is very large, tends to infinity, and the inside and outside radius are same. That is, the inside tube is having negligible thickness. So under such condition, overall heat transfer coefficient 1 over U is equal to 1 over Hi plus 1 over Ho, where Hi and Ho are convective heat transfer coefficient of inside and outside fluids respectively. Case number 2, U is dominated by smaller convection coefficient because reciprocal of smaller value is very large. So if convective heat transfer coefficient of inside fluid is smaller than the outside fluid, so overall heat transfer coefficient will be governed by the convective heat transfer coefficient of the inside fluid, because Hi is smaller, So its reciprocal will be large and overall heat transfer coefficient will be approximately Hi, which happens to be H is smaller in this case. Case 3, if one side of the fluid is gas, let's say inner side, and other side it is liquid, that is outer side. Under such condition, to improve heat transfer coefficient on the gas side, sometimes fins are introduced. So fins are used on gas side to enhance product of U into A, that is overall heat transfer coefficient and surface area. Under such condition, the relationship between U and total thermal resistance will become like this. 1 over Ui Ai is equal to 1 over UOAO is equal to 1 over eta I into Hi into Ai plus log of Rho over Ri over 2 pi Kl plus 1 over eta O into Ho into Ao, where eta is the fin efficiency. So it depends upon which side of the fluid we provide fins. Accordingly, fin efficiency will come into picture. So if tube is finned, the total surface area on the fin side will be given by eta into fin into area of fin plus area of unfinned portion. Now typical values of overall heat transfer coefficient. Irrespective of the types of heat exchanger, overall heat transfer coefficient will be minimum for the heat exchanger which facilitates the heat exchange between gas and gas, and this value varies from 10 to 35 watt per meter square Kelvin, whereas overall heat transfer coefficient U will be very high for the heat exchange between two liquids, values ranging from 300 to 1400 watt per meter square Kelvin. Next very important phenomena which is occurring in case of heat exchanger is called as fouling. Now heat exchanger and its heat transfer surfaces are often subjected to deposition of fluid impurities like scales, algae, bioproducts, rust formation, and the heat exchanger surface may become corroded as a result of this interaction or reaction between the fluids flowing and the material used for the construction of the heat exchanger. So fouling is defined as the deposition and accumulation of unwanted materials such as scale, algae, suspended solids, rust, and insoluble salts on the internal and external surfaces of process equipments like boilers and heat exchangers. This coating offers an additional resistance to heat transfer between the fluids and thus results in decreased performance of heat exchanger. The scale or coating deposited is generally of insulating in nature and it resists the heat transfer between hot and cold fluid, which ultimately decreases the performance of heat exchanger to transfer heat between hot and cold fluid. The overall effect of this scaling and fouling phenomena is approximated by including one more resistance apart from what we have discussed in the previous slide, called as fouling factor or fouling resistance, and it is generally represented by capital R suffix small f, RF. The value of this RF depends on operating temperature of the fluids, video velocity, that is moving velocity, and length of service of heat exchanger. So as you can show in this image, a fouled heat exchanger is shown in this image, where scale, the metal tubes are get corroded, rusted, scale deposits are there, and because of this the heat exchanger is not in the position to transfer the heat between hot and cold fluid effectively. It is fouled so badly that it has to be decommissioned from its service. This image source is from Temco and this is its link. Thanks to Temco. Now fouling can be reduced by applying following methods. Fouling is totally undesirable phenomena. So we must reduce fouling and its effect to enhance the effectiveness of heat exchanger. Number one, the most common type of fouling is deposition of solid particles suspended in the flowing fluids. When water used in a heat exchanger is hard, the scales are formed and hence treated water must be flow through the heat exchanger. So this way we can reduce the fouling if water is used as a fluid. The scale of solid deposits can be cleaned by scratching and chemical treatment of surfaces. Other method is the corrosion and other chemical fouling are common in chemical process industries. Such type of fouling can be eliminated by coating metal pipes by glass layers or by the use of plastic pipes. However, this method may affect the heat transfer rate between hot and cold fluids due to low thermal conductivity of pipe material as compared to the metal pipe. Now, fouling is totally, as I have discussed, is a undesirable phenomena. So fouling and its effect can be ascertained by calculating the value of fouling resistance. And fouling is generally in the form of scales, rust or algae formation, and they are deposited on the cylindrical surface of some thickness in the form of certain thickness. So in order to calculate their effect, thickness of the scale and its thermal conductivity must be determined. However, the thickness and thermal conductivity of the scale deposits are difficult to ascertain. So, the effect of scale and fouling on heat transfer is considered by specifying an equivalent scale heat transfer coefficient H suffix S. If HSI and HSO denote the heat transfer coefficients for the scale deposits on the inside and outside surfaces of the heat exchanger respectively, then the thermal resistance due to fouling on inside surface can be given by RFI is equal to 1 over HSI, and thermal resistance due to fouling on outside surface, please read this as outside surface, RFO is equal to 1 over HSO. So this way we can calculate thermal resistance, that is RF is equal to 1 over HS. So let us first calculate overall heat transfer coefficient for plain wall heat exchanger. If the heat exchanger is in the form of plain wall of area A, thickness L and thermal conductivity K, then relationship between U and R total will be U is equal to 1 over A into R total, where A is the area of the wall normal to heat transfer. So in this case, U is given by U is equal to 1 over A into 1 over HIA plus 1 over HSI into A plus L over Ka. This will be conductive thermal resistance offered by plane wall plus 1 over HSO into A plus 1 over HO into A. Let's say this side is hot fluid and this side is cold fluid. So heat transfer will taking place between hot to cold fluid through this plane wall heat exchanger. So total thermal resistance will be this much. And scale deposited on this side is, and this side is, so total thermal resistance will be given by this expression. In this expression, 1 over HSI into A plus 1 over HSO into A. This represents convective or fouling resistance of scale deposits on the inner side and outer side of the heat exchanger. Now once again 1 upon HSI is equal to RFI, or simply 1 over HS is equal to fouling resistance. So expression for overall heat transfer coefficient for this plane wall will be reduced to U is equal to 1 over HI plus RFI plus L over Ka plus RFO plus 1 over HO. So this expression will take into consideration the effect of fouling resistance on the overall heat transfer coefficient. Now overall heat transfer coefficient for tube or cylindrical shape heat exchanger. So same expression I am going to use, representing relationship between U and R total. U into A is equal to 1 over R total. So let us consider once again this cylindrical tube-in-tube heat exchanger, where inside tube is carrying hot fluid and outside tube is carrying cold fluid. So relationship between inside and outside based overall heat transfer coefficient as UIAI is equal to UOAO is equal to 1 over HIAI. This will be convective thermal resistance offered by inside fluid plus 1 over HSI into AI, thermal resistance offered by scale deposited on the inner side of the inside tube plus 1 over 2 pi KL log of RO over RI. This is the thermal resistance offered by cylindrical wall plus 1 over HSO into AO. Once again, this is the thermal resistance offered by scale deposited on the outer side of the inside tube plus finally 1 over HOAO. This will be convective thermal resistance offered by outside fluid. Since 1 over HS is equal to RF, so UIAI is equal to UOAO is equal to 1 over HIAI plus RFI over AI, replacing 1 upon HSI as RFI plus 1 over 2 pi KL log of RO over RI plus RFO over AO plus 1 upon HO into AO. Once again, these two terms are introduced to take into account the effect of thermal resistance or fouling resistances. In this expression, AI is pi DIL and AO is pi DOL, where DI and DO are inside and outside diameter of the inside tube respectively. So overall heat transfer coefficient based upon the inside area of the tube UiAi will be equal to 1 over HiAi plus RFi over AI plus 1 over 2 pi KL log of RO over Ri plus RFO over AO plus 1 over HO into AO. Multiplying this inside area to this entire expression will give me this expression for overall heat transfer coefficient based upon inside area. Similarly, for the overall heat transfer coefficient based upon the outside area, UOAO into total thermal resistance offered to the fouled heat exchanger. Multiplying this AO to this expression, I will get UO equal to 1 over RO over Ri into 1 upon Hi plus RO over Ri RFi plus RO over K log of RO over Ri plus RFO plus 1 over HO. So this way one can calculate overall heat transfer coefficient for tube or cylindrical shape heat exchanger based upon inside area or based upon outside area. Please remember, product of Ui into Ai will be equal to Uo into Ao, but Ai is not equal to Ao and Ui is not equal to Uo. Now, fouling factor can also be determined experimentally by determining the overall heat transfer coefficient for both clean and dirty conditions in the heat exchanger. So first we can calculate overall heat transfer coefficient for clean heat exchanger, then finding out its overall heat transfer coefficient after fouling. So RF will be equal to 1 over U dirty minus 1 over clean. So this is another way, but this is quite difficult. So after watching this video, you will be able to discuss and evaluate overall heat transfer coefficient of heat exchanger. You will be able to define fouling and its effect on overall heat transfer coefficient. So with this, I come to an end of this video lecture. Thank you for passionate listening. Happy learning.